Hello everybody, I am Zach Peterson. Welcome back to my channel. Today I'm going to be talking to all of you about S-parameter reciprocity and how it relates to impedance matching. S-parameter reciprocity is an important topic in high-speed PCB design and RF design because it describes how signals propagate in forward direction and backward direction along a circuit or along a transmission medium. First things first, we're going to get on the whiteboard, look at some concepts around S-parameter reciprocity, and then we're going to take a look at some simulation results to really test how impedance matching affects S-parameter reciprocity. Let's go ahead and get started. So the topic of this video is S-parameter reciprocity. And so for those of you out there who are not signal integrity experts, you may be wondering, what is S-parameter reciprocity? Well, S-parameter reciprocity has a very simple meaning. Essentially, what it means is that the transmission S-parameter, S21 magnitude, is equal to the transmission in reverse direction, S12. So, for example, if we have a two-port network, it doesn't matter which direction a signal travels in that network, you will get the same amount of loss whether you go in the forward direction or in the backward direction. So just as an example, let's draw out a simple two-port network and what we would expect to see in an S-parameter plot. So here we have our port 1. We'll just draw it like a little rectangle like this. And let's just suppose this is a transmission line with characteristic impedance Z0. And then we have another port here, port 2. And then these are both referenced to ground. Very simple two-port network. This could be a differential port or it could be a single-ended port. Doesn't really matter. What matters is that we do have some S11 right here at the input of port 1, and then we have some S22 right at the input of port 2. And then during propagation along port 1 to port 2, or in the reverse direction, we have an S21. This would be transmission from port 1 over to port 2. And then we have, in the reverse direction, a S12 S-parameter. So this is our set of 4 S-parameters for this simple two-port network. Now, what would we expect to see on a graph of the insertion loss and the return loss? Well, let's take a look at the return loss first. Now, if we have S11 and S22, and the reference impedance and the terminating impedance at the two ports is the same, then we would expect these two curves to basically overlap each other. So you might get some peaks and valleys like this, and this would be your S11 curve and your S22 curve essentially overlapping each other. Now, what about our insertion loss curves? Well, with our insertion loss curves, we would basically expect the same thing. We would basically have something with an S21 curve that maybe looks something like this, and then we would have our S12 curve also lined up right on top of it, okay? So again, S21 equal to S12 essentially implies that this holds for all frequencies, not just at one frequency. And this is why these curves would overlap each other, as you see here. Now, what about the case where we have an impedance mismatch at different ports? Well, I think your intuition would say that because there is some asymmetry in the system and we have an impedance mismatch at one port that does not match the impedance matching at another port, so we have a reference Z1 and a reference Z2 that are different at different ports, we might expect that the reciprocity relation does not hold. So what would we expect in that case? Well, in that case, we're going to have an S11, which I'll draw here in red, and the S11 curve that you see here that I'll draw in red, maybe it looks something like this. So this is our S11 curve. Now we also, again, have an S22, and I'll draw it in blue. Our S22 curve might also look similar, but it doesn't perfectly overlap anymore. and this is our S22 curve. So this is pretty standard when you have different impedance matching conditions at the two different ports. If the input impedance looking here is different from the value of the input impedance looking here, then these two curves are not going to overlap. So I think intuition tells you that the S21 and the S12 curves also don't overlap. But if we have a truly reciprocal network, that's not what happens. If I were to draw out the curves for S21 and S12, we would have curves that basically also look like this, perfectly overlapping in the case of a truly reciprocal network. So this is, I think, a bit counterintuitive to some people because, again, we might expect that because we have different levels of reflection at the two ports, we would also expect the insertion losses to be different. So can we check this with a simple example in a simulation program? As it turns out, we can check it with a simple simulation. We're going to go ahead and do that in Simbeor. And what we'll do is we'll do a simple simulation where we have the same impedance mismatch at the two ports, and we'll look at the S parameters and see whether they overlap. And then we'll enforce different impedance matching conditions at the two ports, and then we'll see if these S parameter curves for the insertion loss change once we change the impedance matching conditions at the different ports. So let's go ahead and hop on the computer, take a look at a Simbeor simulation and see if this actually holds. Now here I'm inside of Simbeor and I've pulled up the model that we used for the length tuning impedance video. And if you haven't seen that video, check out the link in the description and you can go and watch that video and learn all about mode conversion. Now what I want to do here is just build a simple model for this transmission line. And the first thing we're going to do is just check the differential impedance. And you can see here the differential impedance coming out to 90 ohms when we look at these results here from the ERC test. Now here what I want to do is to create a signal integrity model for this differential pair. And you can see here I have the I/O configuration tool up. And what I've done is I've set the termination resistance here to 100 ohms, which is the default value for differential pairs. So here we have 100 ohm termination resistance set on port 1, which is over here on the left, and on port 2, which is over here on the right. Now the reason we're enforcing just a little bit of mismatch here is so that we have some features we can look at in the return loss spectrum, and then we'll go back and we'll modify this termination resistance at one of the ports to see how the overall S parameters change after that modification. So let's go ahead and build that model, and then we'll go ahead and extract the measurements. We're going to plot the insertion loss and the return loss, and we're just doing a fast SI simulation here. You can see that it finishes pretty quickly. Then what I want to do is go ahead and pull up some of this data for our return loss. And you can see here the return loss at the two ports is shown on screen. Now you can see here we have a little bit of a difference in these two curves because we do have this length tuning structure here inside of this differential pair. So as we would expect, of course, it does create a little bit of impedance deviation at certain frequencies. And you can see that very clearly by looking at these two curves on the same graph. Next, let's take a look at the insertion loss plot. So you can see here in the insertion loss plot, we have the S21 S parameter plotted, and then we also have the S12 S parameter plotted, and these are both, of course, the differential in, differential out ports, as you can see here on screen. And it's very clear that the two curves exactly overlap. So you can see here the circle symbol and the star symbol, they all coincide with each other all the way across this graph, as we would expect, because we do expect transmission lines to be reciprocal systems. So now let's go ahead and go back to this simple model, and we're going to build a new model here using the Fast SI tool. And here what we're going to do is we're going to set the impedance at port 2, instead of being 100 ohms, we're going to set it to 85 ohms. Now, we're enforcing different levels, both magnitude and direction, for the impedance mismatch at the different ports. And we're going to go ahead and build that model, and then we will also extract the insertion loss and the return loss from that model. Next, let's go ahead and look at the return loss. And again, you can see here the return loss is different for these two cases As we would expect, the return loss seen at port 1 is slightly different from the return loss seen at port 2. Again, of course, we would expect that because we do have the length tuning structure, as you can see here in the model. But also, when we compare these to the previous case where we had the same impedance mismatch at both ports, it is also different from that case as well. So you can see here as I flip back and forth between these two return loss spectra, you can see that they are quite different. Now let's look at the return loss plot. So here I have the return loss plot open, and I'm going to add the S12 S parameter to this return loss plot. And you can see here when I add this, you don't see it anywhere on screen. Well, that is because the S12 S parameter is perfectly overlapping the S21 S parameter, as you can see here on the graph. So they totally overlap each other, and you can actually see here that they have the same symbol, and that's why you don't see any differentiation between them in this plot. Now, if I just delete this red curve, you can see here the blue curve appears. So that's your proof that they actually do perfectly overlap each other. So even in the case where we have different values for impedance mismatch at the two ports, where we have 100 ohms at the left port and 85 ohms at the right port, we still have reciprocity enforced because the reciprocity is seen in the off-diagonal S parameters, not in the diagonal return loss S parameters. Well, there you have it, folks. As you can see from the simulation results that we did in Simbeor, it is very clear that S parameter reciprocity in a linear system is not broken simply due to different impedance matching conditions at either end of the interconnect. This is because, as I mentioned, the media that make up printed circuit boards and packages is linear. It is not anisotropic. It doesn't vary with the intensity of the wave traveling through it or any of the other factors that could produce nonlinearity. And this is why we only need to look at the S21 plot when we are looking at S parameters and doing some S parameter analysis. Just remember, in active circuits like RF circuits that have gain, you could have breaking of S parameter reciprocity because now the amount of signal that you transmit along either direction could be a function of the input signal strength. If you enjoyed this video, make sure to hit that subscribe button, leave your comments and questions in the comment section, and I'll see you next time, folks.